Okay, I think I have started the recording. So let's start. Um, Let me briefly introduce about today's speaker. So today is the first talk we have at UCF Computer Architecture Seminar Series this semester, and our speaker is Mr. Gaurav Jain. Uh, Gaurav is a software engineer at D-Matrix, where he's leading the effort for building the kernel software stack for next generation in-memory compute LLM inference hardware. Along with this, he's also involved in the research and the exploration of technologies aiming towards the improvement of end-to-end model performance and reducing memory overhead. Prior to this, he was a silicon architect at Google Pixel TPU machine learning accelerator team, where he day-to-day activities involved architectural specification, performance modeling, and the workload characterization for Google's machine learning workloads. Gaurav holds a master's degree in electrical and computer engineering from the University of Wisconsin-Madison. So his research interest spans across multiple domains, including model optimization, machine learning system, hardware, software co-design, and computer architecture. So take it away. It's yours.
Sure. Thanks, V, for the kind introduction. Hey, everyone. I'm Gaurav, and today I'll be talking about all the stuff we are doing at D-Matrix to take generative inference from unsustainable to attainable. Thanks for taking out the time to be here, and I hope that by the end of this talk, I'm able to convince you that a chiplet-based in-memory compute solution is the most rational way to do generative inference. So here's the agenda of my talk. Like I'll be starting with, uh, sorry, is the slide changing on your end?
Yeah, it is.
Okay, great. Yeah, it didn't show up on my great. So yeah, here's the agenda of my talk. I'll be beginning with going over the well-known problem of large language models, and from there and the memory wall. And from there, I'll be delving into what D-Matrix is doing to solve these challenges by designing a first of its kind data center scale chiplet-based in-memory compute solution and a corresponding software stack that makes serving these LLMs affordable and efficient. And I'll end the talk by going over one of our previous projects we did for reducing the footprint of memory footprint of KV cache. So let's dive right in then. Wait, I think there's some lag. It's not changing on my end. So I would again confirm. Is it changing on your end? Like
I
on,
saw the memory wall and the
yeah,
large
okay,
language
great,
model slides.
great, okay. Yeah. So here's an image of what we have seen plenty of times in the last couple of years, and a fact that we have known for almost 3 decades now. This plot here shows us the growing disparity between the processor speed and the memory speeds, and how the AI era has only exacerbated these problems, where the disparity has become a critical bottleneck in computing performance and power efficiency. The disparity is staggering today, and if we don't do anything soon, the gap is only ever going to increase. If you see over the last couple of decades, the increase in flops has been almost about 3x per 2 years, versus the increase in DRAM bandwidth only been about 1.5 times over 2 years, and the interconnect bandwidth has been even lower. So, and can you believe that this was coined in 1995, and it still bothers us today to date? So over the last few years, what we have seen that there's been a trend in the industry in terms of developing compute systems for AI workloads, with the belief that AI workloads are a compute problem. And most of the area of focus has been to build larger and larger systems. But we know, and research has shown in plenty, that LLMs are not just a compute problem. In fact, LLM inference is as much, if not more, a memory bandwidth problem. LLM inference in general exhibits behavior where the reuse for every byte of data ordered from the off-chip memory is low, thereby resulting in a very low arithmetic intensity. And this formula over here tells what arithmetic intensity is. So what this means is that for every byte of data we get from the memory, the processor only has low reuse for that. That is, it performs a less number of operations. And this problem only worsens as the distance between the processor and the memory grows, and the bandwidth doesn't keep up with the increase in processor speeds. Another important implication of these prohibitively large compute systems is the power draw. Talking about power consumption is a topic that would consume almost half a dozen such sessions, so I'm mostly skipping it in my talk today and would just like to say that a chiplet-based in-memory compute system should solve a lot of those challenges at scale. So now that we have seen that the baseline about memory wall, let's quickly switch gears and talk about why the memory wall is an issue for large language models. First, let's try to understand what large language models from an architectural perspective are. They are nothing but a series of matrix or vector matrix multiplications put together with some interleaving nonlinear operations. Another thing I would like to mention over here is that for the purposes of this talk, like and primarily as D matrix, we are focused on serving large language models at scale. That is, we are focused on efficient large language model inference. So I'll mostly be discussing the implications of large language models and architectures from the perspective of what we see at inference time, and skipping over like all the complications that come during training time. So with the architecture we saw for the large language models in the previous slide, this slide just shows that how these layers are stacked up together to and work in tandem to create what we call token generation. Say you go to Gemini or Chat GPT and ask a question, and a few moments later it starts generating response. The question you just asked to Chat GPT is what is generally known as the pre-fill stage or the input system plus user prompt, which is the phase you see on the left. And the response which the system starts generating for you is called the decode stage, that is the token generation stage. And this is what you see on the right. So in general, the input prefill phase is where all of the tokens are available for the system at once, and you can efficiently utilize and saturate the GPU computing power. Whereas in the decode stage, you would see over here, what you're generating is you're generating one token at a time. And this happens because to generate every new token, you need to be able to visit all the tokens that have been seen in the past. You sample on them and then generate a new token. These are primarily vector matrix multiplications compared to the matrix multiplications you see on the left. Now, what are the implications of this? How does this affect the overall processing of token generation and efficiency? I'll be going over that in the next few slides. But first, let's look at an example of what's the prefill stage and what's the decoding stage. So I went to ChatGPT. I asked a question that give me a 5-day itinerary to south of France in September. So it did some tokenization, and this is the GPT-4o tokenization you're seeing on the left. It broke my input prompt into 24 tokens. Now these 24 tokens then ended up generating almost 600 tokens in response. It came up with a detailed itinerary of what I should be doing in September. But if you see that these 24 tokens on the left can actually be processed in parallel because the system knows about them at once. Whereas on the right is what you see that these 600 tokens in its most naive form are generated sequentially, that is one token at a time. And this is where most of the time is spent for an LLM inference. In fact, this problem is the time taken during the generation of these tokens is so much so that these are some excerpts that I've taken from industry and research papers where they say that it takes all the decode cost of generating one token can be at as high as 200 times the prefill cost per token. And then the other statement says that for every 100 tokens have the same impact on latency as a single output token would have. So the obvious solutions which you can come up from here is either you increase the cost you pay for token generation, you reduce the token output length, or you just wait longer for response. But I'm sure none of us want to do that, right? So we have seen the importance of performant token generation. So let's quickly go over some metrics that quantify and are vital to provide a seamless end-to-end inference experience to a user. The reason to bring these up here is because I want to stress on the numbers that we talked about when we talk about LLM decoding. it's not just the throughput that we should be focusing on. We should be looking at latency. We should be looking at what's the time you spend per token generate and per user, because we can obviously batch, but it's important to focus on a per user experience and the overall latency it will take for the model to generate the response for that particular user. So yeah. So this figure you see is very similar to what we saw a couple of slides before. The one on the left is the prefill stage, which we talked about. And as we see that all the input tokens are present at once, and this can very well be made a matrix multiplication operations. Whereas on the right is what you see a vector matrix multiplication operation, where decoding happens one token at a time. These vector matrix multiplication operations have a very low arithmetic intensity. And we know what arithmetic intensity is. It's flops for memory ops, right? And the reason for this low arithmetic intensity is because in its naive form, for every token you generate, the entire context is brought from the memory to the processor. A vector matrix multiplication operation is performed and a new token is generated, and the context is written back to the main memory. Now, if you were to do this every token iteration, you would be spending a lot of cycles just going back and forth between the memory. So what would you do to try to improve the arithmetic intensity? One obvious thing is, and which we have seen in AI workloads and non-AI workload applications, is you just increase the batch size. By increasing the batch size, you have more work you can provide to the system to do, and thus improve the overall hide the latency which you would be spending on bringing the data for the next iteration. However, in the case of large language models, it's not straight, and especially inference, it's not as straightforward. The reason for that is that large language models also come along, apart from the large model size, they also come along with a thing known as KV cache. Now, what KV caches are and how they impact the overall memory footprint, I'll be going over that in the next couple of slides. But for now, let's assume that yes, KV caches have a high memory footprint, and because of that, increasing the batch size might not always be the best solution. And the graph over here actually corroborates the fact. If you see this figure on the right, what you see is that as you're increasing the batch sizes, you are actually able to see improvement in arithmetic intensity, which is what we would have expected, right? Now, but as the batch sizes go beyond a few hundreds, in this case, I think somewhere around 100 to 200 range, depending on what model and context size we are looking on. But as the batch size goes on increasing, the arithmetic intensity just plateaus. And why it plateaus? This is due to the fact that as you're increasing the batch sizes, the amount of data or the amount of data and how frequently you need to go to the main memory also increases, and it increases significantly, because of which you are no longer able to hide the latency which you were able as you were able to in this first half of the graph. And now going back to KV cache, what KV caches are? KV caches are reserves of memory that stores all the tokens that we have generated up till now. Why they are important is because in a naive large language model, if you were to generate a new token, you would look at all the tokens you have seen in the past, you would process them, sample on top of them, and then generate a new token. Now, all the tokens, what you have seen in the past, either you can obtain them in two ways. Either you store them as you're generating, or you recompute them every time you have a new token to generate. So I'll not be going over why recomputation is not done or how it's a problem in general. I'll be sticking with the concept of talking about KV cache, because this is more or less what everyone in the industry and academia uses and makes sense also. Whatever you have generated up till now, you would be storing that in the memory, and the next time when you need it, you would just fetch it from the memory, do the set of vector matrix multiplication operations on them, and write it back to the main memory. So what you have done is that you have started creating a cache of all the tokens you have seen until now. Now the question is, and this is an active research problem, is that do you need all the tokens which you have seen? We know that it's not the case always, but for now, let's assume that we'll be using the system needs all the tokens we have seen till date. So let's look at what's the impact of KV cache. If you see on the graph on the left and in the right, they both establish the same fact that as your sequence length increases, depending on the model size, the batch size, the KV cache required also increases, and it blows up very quickly. So when you were dealing with the sequence length of 256, for example, on the left, on the graph on the left over here, the overall memory footprint was somewhere around 50 gigabytes. But as you increase the sequence length to 8K, you see that the overall memory footprint goes almost up to 250 gigabytes. Now imagine going back and forth, and this is corresponding to a batch size of 64. So as you're increasing the batch size, your memory footprint is increasing. So, like how many cycles you have to hide before you can actually, how many memory cycles you have to hide over here significantly increases, and your memory bandwidth starts becoming the bottleneck again. That's why we saw that the arithmetic intensity starts to plateau very quickly. So and the graphs on the left show the impact on the inference latency as well. So now let's get to what D-matrix is doing about it, right? First, let's talk about the memory bandwidth impact we have seen. We have seen that memory bandwidth results in low arithmetic intensity, especially during the decoding state of LLMs, right? Many techniques have been proposed in literature and in industry. Things like doing low precision inference, quantizing your models and model weights and KV caches, doing model compression, operator fusion so that you can have less back and forth between the memory, and many more. But we have to understand that the traditional von Neumann bottleneck still remains. And the one of the obvious solution is, can you bring the compute closer to the memory? Now that's where we at D-Matrix have this new paradigm called compute in memory. Now this figure over here shows that, and this is from one of the recent stats which we see, that even if you have state-of-the-art HBM, the bandwidth which you have between the processor and memory, you can only achieve up to 8 terabytes per second. Whereas if you were to bring the compute closer to the memory, you can instantaneously increase that to 150 terabytes per second. So that's almost 15x improvement in the memory bandwidth by just bringing compute to the memory. While I'm saying it's by just bringing compute to the memory, that's a technological challenge in itself, and that's what the team at D-Matrix is solving, and in fact, like, has solved by over last couple of generations by taping out the chip as well. So let's quickly go over what are the advantages that we see by having compute in memory, right? So one obvious advantage is that it integrates the computation directly with the memory array, thereby addressing the limitations of von Neumann architecture. You do not have the memory and the compute separate anymore. This minimizes the need. This reduces the data moment. That is, it minimizes the need for data transfers by performing computations where data is stored. Obviously, you have a backing memory, right? We are talking about doing the digital memory compute over here. So we are talking about SRAM. So you do have a backing memory, which is DRAM in our case. But the number of times you would have to go to the DRAMs can be significantly reduced if your SRAM is large enough, and you no longer have any data movements between where your ALUs are and your SRAM is. This also allows us to have higher parallel processing capabilities. Now, multiple operations can be performed simultaneously across the memory array, and obviously, you take advantages of all the improvements and the techniques which the industry and academia has proposed in terms of operator fusion, quantization, and model compression, and others. Like all of those techniques are still valid. And overall, if you are reducing the data movement significantly, you obviously significantly reduce your power consumption and energy usage. So the bottom line is, digital in-memory compute should allow you reduce data movement, reduce latency, and reduce power consumption. So, but we don't just stop at in-memory compute. We take these in-memory compute chips, we put them in a chiplet-based modular design, because we know that large dies in itself are a pain. They are significantly expensive to manufacture. They suffer from high power consumption. They are susceptible to higher percentage of manufacturing defects. They require complex heat dissipation solutions, and managing interconnects at that scale is hard. It's really very hard. And I think, like, the industry has examples to show how hard it is. Whereas on the smaller dies, we have low rate of failure. Further, adopting this chiplet-based design allows the system to be usable even if one of the chiplets were to suffer from any kind of defect. Then also the chiplet-based design allows us to have a high die-to-die bandwidth, which you see on the right over here. It gives us at almost about 512 gigabytes per second of transfer and receive bandwidth between these dies. This is very vital when we are talking about a distributed inference scenario, because low latency communication is vital, and it allows us to do operations like all reduce, all gather at a very low cost. Then one of the most important advantages of having a chiplet-based design or a chiplet-based in-memory compute solution is that it allows us to scale up and scale out. I'll be going over what scale up and scale out means in the next couple of slides, but this should establish that distributed inference is extremely dependent on all these factors combined, and it's not just one innovation that can solve all the problems. So taking this chiplet design and taking the advantage of high-speed die-to-die interfaces, we have put together multiple chiplets and formed what is known as a card. So this is more or less a logical view of a card. And I think like in this figure, you see almost eight chiplets that have been put here. And each of these chiplets can communicate using the high-speed die-to-die physical links. And then this card can be used to scale up by over multiple cards by using the PCI Gen 5, which gives us almost about 1 terabytes per second of 1 terabytes per second of bandwidth. And on top of that, we can use this to scale out over PCI or Ethernet, and thus create a complete distributed inference solution. So scaling out beyond a single card generally, and that's what we talked about, is done over PCI Gen 5 or Ethernet, depending on what kind of solutions and form factors the end user desires. But all of these to get put together provides us a solution to have to do distributed inference at data center scale. So now we have seen most of the improvements that come along with in-memory compute, chiplet-based design, and then that allows us to scale out. The other thing which we are doing, and which we talked about a few slides ago, was built-in quantization. So we know that quantization and model compression are techniques that can allow us to reduce the overall memory footprint of the models and the KV caches. So if you were to store, let's say you take a 16-bit large array of 16-bit floating point value, FP16 values, you would require X bytes to store them. And if I were to tell you that you have the possibility to compress them into, say, quantize them into int4, int8, or int8, you can immediately reduce the overall size by 2 or by 4 times. And if you also have the capability to do computation in these low precision formats, that also significantly improves your compute cycles, because now you no longer need to go back and forth between these various data formats, right? And with the proper care for outliers during these quantizations and quantization, you can also make sure that you are able to achieve all the desired accuracy. So the reason to bring this up over here is because quantization, storage in quantized format will directly and significantly benefit your KV cache sizes. Because it reduces the overall footprint or the memory storage required for the KV caches. And B, even if you were to go back and forth between the memory and the processor, the number of the memory bandwidth required, or the memory bandwidth pressure, also significantly reduces. So what we have done this at a hardware level is that we have built the hardware such that you can store and compute in quantized formats. So the Corsair D-Matrix Corsair supports industry standard microscaling formats, and these microscaling formats are nothing but like a representation where a block of data, say in FP16, is quantized as scalar elements and have a shared scale value along with them. So let's say if I tell you that you can give me a block of FP16 data, and I can reduce it to, say, 12-bit storage or 8-bit storage. And how I would be doing that is I would be converting that block of 16-bit data into 4-bit scale values, and then also have a 4-bit shared exponent for that, which together will give you a quantized representation for the original block of input data you provided. Obviously, the picking of these scale values are very important because this will directly impact the overall end-to-end accuracy of the model, and also overall end-to-end accuracy of the model. And we have extensive amount of research that has been done internal and across a large scale of models and sequence length, where we have determined different quantization levels for models depending on the data set, the downstream task, and that allows us to achieve significantly high speed up in terms of the compute itself, because now we are no longer operating at FP16 or FP32 scale. So this summarizes more or less like all the high level innovations that have happened to come up with the D-Matrix Corsair hardware. And over the last few years, like there have been different milestones that have been achieved within the company to make sure that all the new technologies that have been introduced are verified and increase our confidence to go to where we want to be. That is, have a full chip that can be deployed at data center scale. So and this picture over here shows like all those different milestones. I think the first one was taping out the in-memory compute, which was called Nighthawk, which was followed by taping out the die-to-die interconnect, which is based on the an open protocol bunch of wires. And then this was followed by another tape out, which used both the in-memory compute, that is and put them in together to form an entire chiplet. Now we are at a phase where we can say where we have confidence enough to work on the chip, and we are in a pretty advanced stage over there as well now. So from here, I will move on to quickly discuss all the different components which are involved in the software stack. But before going into that, let me quickly flash this picture in front of you and talk about just talk about all the optimizations which are required across the entire stack that enable you to interact with systems like ChatGPT or Gemini in an efficient and a seamless manner. Unlike traditional workloads and systems, serving large language models efficiently is a very complex software activity, and this picture exactly shows that. You have numerous optimizations available at every level of the stack. You can talk about model compression, do quantization over there, prune your weights. You can do knowledge distillation, which we are seeing a lot of recent work is involved in. Then at a system level, you have various compiler system optimizations that need to be kicked in. You need to think about doing operator fusion so that you're also reducing the number of trips you're making to the memory. You need to manage distributed inference. Then you also need to look at to efficiently use the underlying hardware optimizations. Like in this case, where we are a chiplet based solution, and we are focused on doing data flow data flow computation, having a spatial architecture. So the software stack needs to be aware and should be able to utilize all the optimizations that are offered by the hardware. So the boxes in the red, which are showing over which I'm showing over here, are some of the optimizations which are natively supported in our stack, and that includes both at the hardware level and the software level. So now let's look at like why the software stack is very important for large language models. So in the last year alone, like in generative AI, we have seen a lot of improvements that have come across the entire ecosystem by companies like by PyTorch, by NVIDIA, by Together AI, and many more companies. And many of these works are focused on publishing research and libraries that allow us to have faster and more efficient inference. And at D-Matrix, we have adopted the same philosophy. We have developed a stack that tries to achieve all of these right from the get-go. So in terms of the compiler and the front-end stack, we are building on top of technologies like PyTorch, MLIR, XLA, a lot of this which are open source, so that we can take advantages of all the work that is being done in the community, and also contribute back to the community. And similarly, on top of that, to be able to leverage all the hardware optimizations which our in-memory compute and chiplet-based system provides, we are building stack that is able to that understands the ISA and is able to exploit all the compute and memory optimizations we have. So overall, like the reason to do this, and in general, like the software stack matters for large language models, is that if it's not properly integrated with the hardware, as in if it's not hardware, if you try to make it hardware agnostic, you will have a very hard time achieving efficient generative AI inference. Because there are certain you have large because large language models in general have large KV caches. You have model weights where you need, if not optimized properly, you would be doing frequent trips to the memory and back. Then you have the case of distributed inference. As you scale out and talk about large cluster inference, you need to understand that your software stack should be able to efficiently execute compute communication overlap. Then you need to also think about at a lower level in terms of advanced kernel techniques, so that you can do operator fusion, which is very important for improving your utilization and reducing your overall latency. And then when you have systems like ChatGPT and Gemini, which are deployed at scale, you have to think about serving multiple users. Then comes in the important concepts like load balancing, managing all the service level objectives, and real time request batching. A lot of the recent works like flash attention, speculative decoding, VLLM, TensorRT, these are all software optimizations that enable the state-of-the-art LLM training and inference. And our software stack is built along a very similar philosophy. So this is the overall representation of the D-matrix software stack. We call it Aviator, and this is a block level representation of the same. So in the middle, you see is the compiler stack, where we have a compiler which is built on top of like open source technologies, like as I mentioned, PyTorch, MLIR, XLA. And on the right, we have the LLM builder, which is a more of a kernel level approach, which we are taking for executing the model efficiently on hardware. Then on the right, there are a bunch of blocks which talk about all the different parts of the software that allows you to serve multiple requests, do distributed inference, then meet your service level objectives, and so on and so forth. Along with this, there is some brilliant work that is done to develop the debugging and monitoring tools, because we know that when working with systems at scale, if we do not have proper debugging and monitoring, and especially performance monitoring tools available, we are essentially going in the blind. And so I'll be quickly going over each of the parts of the stack in short, just to highlight what we are doing in each of these blocks. Let me begin with doing the compiler stack. So on the compiler front, like the most of the responsibilities for the compiler is on the front end we have the PyTorch and the MLIR flow, which then lowers any model which you provide to the hardware native ops. And from there we have the backend that is responsible for mapping and scheduling these ops on the hardware. So when you talk about mapping and scheduling these ops on the hardware, we think about a data flow paradigm, a spatial architecture, where the compiler identifies what are the different kind of operations that can go on in parallel, how are the operations dependent on each other throughout the execution of the graph, and then where are the opportunities that can be fused, and what are the advantages you get by fusing them. Are you reducing the overall the memory cycles which you would have spent otherwise by going back and forth? And it also gets further more complicated, because you just in like if you look at any spatial architecture today, you just don't have one kind of memory registers. You have wait memory, you have activation memory, then you have internal registers for the processing elements. So your backend compiler needs to be aware of all these hardware level details, and needs to have a mapping and scheduling algorithm that takes into account all of these. So, and one thing which I think I haven't mentioned until now is like we have a graph compilation approach overall. And one of the primary reasons to do the graph compilation is, as you would have also read online, is that when you're doing large language model inference, you are working with a philosophy where you compile once, deploy it on the hardware, and then you can serve hundreds of millions of users consecutively by deploying it only once. In that way, you are avoiding your repeated trips to the host and not waiting for kernel launch execution anymore. Along with this, the compiler stack is also built from ground up to level to account for all the dynamically changing tensor shapes. And this becomes of primary importance because, as you saw, that the KV caches, which essentially, if you look at it from a tensor perspective, these are nothing but tensors, and their size increases by one every token iteration. So your software stack again needs to be aware of all the model level features also, because if you're not optimizing for them, then you're again leaving a lot of performance on the table, right? So so this slide summarizes what are the primary responsibilities our compiler stack takes up. Now, before we go into talking about how we then scale this out to serve distributed inference at scale, let me quickly go over a couple of terms which are very widely used in the industry today. One is pipeline parallelism, and the other is tensor parallelism. These are largely used and known techniques. These were proposed in a couple of great works in the past by NVIDIA. In I think it's Megatron. And what they essentially mean is that given a system of nodes, you can partition a model in various ways so that you can in different ways. And the reason to do that is because in general these models cannot fit in one node, right? If you, let's say, just talk about Corsair hardware, Corsair card, we have 2 gigabytes of SRAM memory. And if you want to operate completely out of the SRAM, we can't really do that even with a small model like Llama 8 billion, right? And if you might have to quantize it to 4 bits, and even then you are not going to be able to serve the model because the KV cache also starts coming into the picture. And that's where we need to have a scale out feature, a scale up and scale out feature built natively in the system. And that's what our philosophy is as well. By putting a bunch of cards together, what we can do is we can partition the model across the layers, which is what pipeline parallelism is, and partition the internal tensors across these different cards, which is what essentially tensor parallelism is. And by doing this, you can have a system that operates completely out of SRAM memory. That is, you get 150 terabytes per second of bandwidth, and achieve your goal of distributed inference. To enable these techniques is what our execution stack is focused on. So we saw the different components which are involved in the execution stack. So there's the host runtime, which the inference engine and the chip firmware. These primarily work in tandem to give you to serve any to process any inference request. Now, how if you were to draw industry parallels to this, I would quickly talk about I would quickly ask you to think about what TensorRT LLM, TensorRT, or the and the Triton in technologies like VLLM and Triton Inference Engine do. So what these allow you to do, and I'll go on the next slide, is that it allows you to serve multiple users at the same time by employing technologies like batching, and there you have continuous batching, then allowing you to do dynamic KV caching, then supporting works like page attention and much more. So all in all, what this allows you to achieve is that you can serve multiple users on your system at the same time, and the user doesn't really have to bother about how their inferences are being processed, and the execution stack actually takes care of that. This picture below shows one mechanism of what the execution stack might do. You can have multiple users that over here, like use cases where one of them has an offline inference use case, and the other has an online inference use case. From there, and these could also very well be different models. These could be vision models or language based models, right? So we have a distributed inference orchestrator which would determine which system to launch which request on, because once we have deployed the weights on a set of systems, we know that, okay, see, cards 0 to xn, for example, are going to process something like a large language model, whereas a set of other systems would be focused on serving vision language models, right? And then you also would want to serve multiple users. So, and one of the requirements in general we have seen is that a user doesn't want to wait for their query to be served, right? So what do you do when you have multiple users or multiple inference which are already in flight? So that's where a technique like continuous batching comes into picture. What it does is it sees the first available slot that is that is free and puts in this new request in there. So, and I'm saying like it's very simple to do that when you think about it like that. But in the backend, there are a lot of complexities you have to take into account. If you go back all the way to the different stages which we are talking about for an inference pipeline, you know that there is a prefill stage and a decode stage. These itself have different characteristics. And if your inference engine and your runtime is not aware of these different characteristics and doesn't schedule these requests accordingly, you are going to again take a hit on performance, like, and suffer from high latency. So this overall, like until now, these different parts of stack which I went over, overall, I think summarizes the software stack which we call as Aviator software stack at D-Matrix. So from here, I would quickly want to jump into what we are doing in terms of research at D-Matrix. So in this, I will be only talking about one of the works which we did last summer with an intern, but this in no way like is an exhaustive picture of what's happening what's happening within the company. This summer alone, we had almost 10 plus interns, half of whom were graduate PhD students who were working on exciting topics which are primarily focused on pushing the large language model inference to the next level, right? So now going back to the topic in focus. So this was the work which was published this year in MLSys 2024, and it's called Keyformer. The overall idea is to reduce the KV cache, right? If you remember what I mentioned, that in general, like in its most naive form, whenever you want to process a new token, you would have to wait for the entire context to be available and sample on that. But in this activity, we realized that that's not really the case. Let me quickly jump to that. Yeah. So let me quickly jump to this figure and show that in general, you don't really need your entire context and you don't really need to sample on that. In fact, like 90% of your attention score is distributed across just 40% tokens. So now the key research becomes, how do you identify those 40% tokens? And more importantly, how do you make sure that the 40% the set of tokens that you discarded because you determined that they are irrelevant are continue to be so as you're making forward progress, right? Because you don't want to arrive at a point and say that, oh, there is some key piece of information that I dropped in while I was discarding a set of assumingly irrelevant tokens, and now I'm generating response that is not desired, right? And the another key insight over here is that, like, that you need to scale your attention as well. If you I didn't go over into in the in detail about the overall architecture, but there is a softmax operation that happens in the attention block, and all that the one of the primary things that softmax does is that it ensures that it normalizes your weights, right? It normalizes your activations. And during the normalization process, what it does is it ensures that your overall probability is sums up to 1. Now, if I discard some tokens, right? Let's say I discard these 3 tokens over here and this like penultimate token over here. You would have to scale the factors of your other tokens so that you are again summing up to that probability of 1. Because without that, and we verified that empirically and through experiments, that without that, the model suffers significant accuracy drop. So I'll quickly so you can read the paper up and I'll share the link to it. I'll quickly go over the results and a conclusion from this. So what we concluded is that all the recent works had a hard time trying to reach the desired accuracy levels by dropping even 10% of the KV cache. And by 10%, I mean, like, let's say you had about 1 gig, like 1,000 tokens you were storing, and you discard 100 tokens of that. Your models were having a hard time trying to achieve the desired accuracy. And by desired accuracy, I think in this we have 99%. And in the paper, we have also talked about achieving the 99 ML perf defined 99.9% accuracy. But with the scaling of softmax, what we employed a technique called Gumbel softmax. With the scaling of softmax, we were able to establish that by even having 50 or 60% of KV cache, we can A, maintain the accuracy of the system, and B, reduce the overall memory footprint of the system significantly. So This is one of the research works which we did last summer, and this was published this year in MLSys. And these are the overall results which we found in that work. So we did some comparisons with the state of the art work then, which was H2O, and then also with full attention, obviously, with the scenario where you're not dropping any tokens at all. And we show that like with even with 50% of KV cache and with the key former technique, we can actually hit the desired accuracy levels. So with this, I would like to conclude my talk by saying that there are different components which are working together in the overall D matrix stack, which allow us to achieve the performance benefits of at least 3 to 10x, depending on the model and the context size you're dealing with, and to some extent almost up to 20x. Okay, and again, a lot of these metrics are depending on what model sizes you're working with, what are the contexts you're generating, what is the batch size you're working with, and many such more configurations. The second thing which I want to add is that training and inference generally should have a separation of concerns, and they should also be treated as such. The optimizations, the behavior a model exhibits on the underlying hardware requirements for each of them can be different. So why should we go through having low utilization and high costs, right? The other thing is that chiplet-based in-memory compute, and which we went over up till now, is the path and the means is to achieve high efficiency, low power distributed inference. And then this is a plug about that we are always hiring. Please refer to a site over your D matrix careers. There are a lot of open roles across the entire stack. You can work on interesting topics like architecture, and if you're more working on the side of semiconductors, like doing backend hardware RTL design, we have roles over there. And then if you want to work on something related to the software stack, so you saw that how extensive the software stack is. We work on kernels, compilers, and there are multiple teams, and all those roles are posted on our website. uh, yep. So that's all I had from my side.
Okay. Thank you, Gaurav, for the fantastic talk. Shows us a lot about what is happening in D matrix and definitely the potential opportunities in D matrix, which will be really useful for the UCF side and also broader researchers, students. Yeah, so I think now it's question time. Any question from the audience? Yeah, you can either choose to post it in the chat or just turn on your audio. We have the first question here. The first question from the chat is from Marco. The question is one Corsair chip connected to all GPUs since you can do reduce? And follow up is in this case, would bandwidth decrease proportionally to the number of GPUs? And also, could you connect one Corsair chip per GPU, or would that be the purpose?
To understand correctly, like, is the question that can a Corsair chip be connected to a GPU? Is that the question over here? Is Marco on call?
Yeah, sure. I was wondering, yeah, like in your typical use case, how many GPUs would be sharing one chip?
Oh, okay. So this is like separate from a GPU. Like we do not connect with the GPU. On a card, we have these 8 chiplets, and then we connect these multiple cards on a multiple cards with each other over PCI. So we don't bring the GPU into picture at all.
Oh, so it can do all of the attention operations itself.
Exactly, right.
Okay, gotcha.
It's an end-to-end stack where you bring a model and you can serve the entire model on these cards alone.
Cool.
Okay, great. So yeah, we have a second set of questions from Christine Bowles. The first question is what kind of compute is down in memory? Is there any example from the system level? And one at a time.
Sorry, yeah. So I have the question. Yeah, so by what kind of compute do you mean? Like whether it's digital compute or what kind of what?
I guess it's operator. Is it?
Oh, in the sense, okay, like what kind of operations that happen inside the memory? Okay. Yeah. So so we do matrix multiplication. So we have multiply additions which happen in the memory. So you can do all kind of max, and then we also have cores attached with these in-memory compute cores that allow us to do non-linear operations like what you would see in a model in general, softmax, ReLU, GALU, and all those things. Then there's both the weights and the activations are quantized. And in terms of the accuracy, do you mean like because we are doing in-memory compute, or do you mean because we are doing quantization is why you're like you're talking about inaccuracies? Uh,
Hi, Chris. I think that's for your second question.
yes.
Yeah, I meant regarding the because of the in-memory stuff. Typically, I see some inaccuracies because of how you're doing it, how you're doing the in-memory compute by itself. Um,
Uh, so I am personally not aware of this, like in the sense because I am personally not an expert in like in that domain of it, doing that from a circuit perspective. So I would probably like take this to a question up, and I can sync up with you offline. But in general, probably wouldn't be the best person to answer this.
yeah, no problem. Thanks.
Yeah, and that's from assuming that you were talking about like circuit level inaccuracies, right?
Yes, yes. I was talking about circuit level inaccuracies. I think
Yeah.
it's more on the analog side, but maybe
Yeah,
in digital also. I don't know. I don't know too much about it, but that's what I wanted to get a sense of.
right. Yeah, my guess would be the same because we are doing digital in-memory compute. I don't think this has been in discussion, at least not something which I have heard of, but I
Yeah.
can obviously like learn more about it and let you know.
Thanks. Thanks.
And between pipeline parallelism and tensor parallelism, I don't think it's either or. Both of these work together in general. If you see that it depends on what your configuration is in terms of your hardware and the software and the model stack, right? If you have a large model, let's say you're trying to serve a Llama 8 billion, and if I give you a system of Corsair cards, and in this case, let's take a number 8, right? So it depends on so each of these have their own trade-offs. Like if you talk about pipeline parallelism, you know that you are talking about serving a bunch of dividing the overall model into a bunch of stages, right? And each stage will have a set of layers which you're working on. So because inference is generally only about forward pass, so you have to think about that you are going to see bubbles in your pipeline, right? So you need to arrive at that sweet spot where you are okay with the bubbles because you have enough work which is going on, and then the units which you took as doing as one pipeline stage is where you can then do tensor parallelism on. So they both go hand in hand and not like they're not like exclusive use cases.
Okay, great. So is there any more questions from the audience?
Yes, I had a question.
Go ahead.
So I wanted to ask about the design of the cores. Um, I mean, are they only capable of doing integer arithmetic because you talked about quantization, or are they in general capable of doing floating points as well? Is it like like different cores for arithmetic operations with integers and different cores for floating points, or is it all integrated into one? And how do you take care of the nonlinearities for layer normalization and other stuff like softmax?
Right, yeah. So that's a good question. So like the cores are all homogeneous. We do not have separate like floating point cores or integer cores and so on and so forth. And it's slightly more than an integer arithmetic because we natively like if you look at the software stack over here, let me quickly go back to that. Yeah, so we have this model compressor which comes into the system, and there's also a quantization phase which happens on the model where your floating point values can be converted to these like these micro scaling formats. So they are still you can think about it being having a mantis and an exponent for each value over there, right? So the hardware in itself, like the compute units in itself, work on that. So they are aware of the fact that there is a mantis and an exponent associated with the compute that's happening. So that, along with, we also have the capability to do native floating FP16, FP32 operations, which are vital when you're doing non-linear operations like layer norm and softmax. And for that, we have like auxiliary cores that are attached with these in-memory compute cores.
Okay, thank you.
Okay, any more questions? If no question, I have one. So
Sure.
my question would be, I saw you're mentioning the runtime will be deciding how to allocate the workload. So in this case, all the runtime is just saying it dynamically decide what to execute, but all the cores are homogeneous, right? So there's no heterogeneity at all within the chiplet.
So yes, so in the sense that once your model has been deployed, right, you have compiled your model. So in that, you feed in what configuration you're compiling the model for. Say you say that I have a single card system or an 8 card system, and so on and so forth. So the orchestration of the weights has already been decided for you, because in that graph compilation phase. Now, what the inference engine and runtime, and that's what I guess you're talking about the runtime, is like it takes these inference requests, like say you have a bunch of inference requests that come together. So what it decides is that whether it should be waiting for more requests to arrive so that it can batch them together, or whether it should go and deploy them. And then as a new request comes in, it keeps on filling your pipeline so that you're able to utilize your maximum batch size, which you have set for your execution. So, but in terms of homogeneity and heterogeneity, I would say that we like there is heterogeneity from the perspective of your layers, right? You can think about that when you're talking about a decoder layer in general. You have some layers which are pure matrix multiplication ops, where versus some layers like the attention and which are vector matrix multiplication ops. Then you have softmax and ALM and so forth. So at a pipeline stage, I would say that this is more per pipeline you would have a picture, and across the pipelines, because the layers are identical itself, so the work you would be doing would be very identical.
I see. Thanks. Yeah, there's one more question from the chat. Could you please also talk about the reusability and the programmability of the Aviator ecosystem? What is the execution model? Is it the same as SIMT, where you can directly control a group of tasks or threads for execution? I guess that's for what is similar to GPU.
Right. Yeah. So uh, first, I would like to say that we do not have a SIMT-like architecture, like explicitly, that there is no notion of tasks and threads in general. So the programming model is sort of obscure, where we try to think more about it from a perspective, because it's a data flow architecture, right? But GPUs are not. It's slightly obscure, where we try to think about more from the perspective of what are the cores within the system, because in general we have these multiple cores that are put together to form a larger core, and then these larger cores are put together to form a chiplet, and so on and so forth. So I wouldn't compare it with the programming model of what the programming model for a GPU is. But in terms of the programmability and reusability, I would say I would like to understand more about this question. Like, are you talking about the programmability from the perspective of what we can achieve on CUDA in terms of programmability, or can you program the course to do something else? Is that the question?
Hi, Emil. Do you want to expand your question a little bit?
The software stack, as in like, again, what part of the software stack you're okay. So the Python APIs don't really need to care about it. So for example, PyTorch today doesn't do anything at the model level. You don't write, right? These are the number of streaming multiprocessors I want to use, or these are the number of thread blocks I want to use. These are all the levels of details that are hidden from the programmer. At PyTorch, you just say that set the device to CUDA and run this model for inference. And that's what more or less our notion is as well. You can think about it like, and I'm obviously simplifying a lot of details. You have a stack like TensorRT LLM or VLLM that also comes into the picture when you're talking about large language model inference. So we have a similar flow on our end as well. But you can think about it being as simple as set the device to Corsair and run that, and you should be able to do that, because you don't have to. You as a user, probably as a model developer, don't really should be dealing with what happens at a thread block level. And that's where the compiler comes into the picture. The compiler, the graph compiler, which we have today, is aware of all the notions of the from a hardware perspective, and it takes care of what nodes of how the node execution should look like, where should the nodes be mapped to, and in what order they should be like scheduled for execution.
Okay, cool. I think we probably have one last question here in the chat. So is there any plan for training acceleration? And if yes, will any new challenges occur?
Not that I am aware of in the sense in terms of the plan. And obviously, like the challenges for training are there. Like they are different also, I would say. Like you also have to think about you can't now fit the trying to fit the model and the KV cache in the SRAM is one challenge, right? But now when you're talking about training itself requires you to be storing the backward pass. So what do you do? Like all those intermediates in there, the memory requirements immediately blow up. So there are a lot more complications that come over there. And right now, I don't think we are focusing on addressing them in the near future.
Okay, thank you. Yeah, I think that we are done with all the questions. It's a little bit over time, and let's thank Gaurav one more time virtually for the fantastic talk. And feel free to reach out to Gaurav for possible opportunities, of course. And I think that's the end of today's talk. Thank you so much. Thanks, everyone.
Thanks, Dee, and thank you everyone for attending. Thank you.
Okay, so see you next time. Bye.